Hello, ladies and gentlemen. Well, I hope you're ladies and hope you're gentlemen. You could be something else. Pot plant, maybe? Anyway, I'm Zaphod Beeblebrox, and I'm the British Tech Guru. And welcome to the British Tech Guru channel on YouTube. Today I want to talk about navigation. Very important thing, navigation. Otherwise you wouldn't be able to find yourself. Now, you've all heard of the GPS. Who hasn't heard of the GPS? And it's on just about every phone. It's in just about every car. But what is it? Well, it's a series of satellites put up by the American military to help people navigate. In fact, to help the military navigate. Now, the civilian version is accurate to within 20 or 30 feet. The military version is accurate to within 6 inches. There are also other competing versions. The Chinese have Baidu, the Russians have GLONASS, and the Europeans have Galileo. So, all very interesting, and we covered navigation last week, or in the last episode, or rather we covered GPS, satellite navigation, in the last episode. In this episode I'm going to cover navigation by grid coordinates. Now, there are several different ways of navigating. Navigating using plain paper and ordinary geometry is the least accurate. In about 1830, I think it was, or 1870, somebody came out with the Haversine formula. Now, the Haversine formula is way more accurate than a geometric, or using geometry, way more accurate. But that relied on the fact that the Earth was assumed to be a sphere. It's not. It's a misshapen sphere, or an ellipsoid. It's an ellipse, elliptical. In other words, it's shaped like a testicle. There, I said it. And about 1970 something or other, a fellow came out with another formula, and that was way more accurate. And I'm going to show you the difference between all the formulas now, and I'm going to show you which one I'm going to be using in the drone project. This is a very slightly different video from the one I've been doing, because I'm not pulling up Thonny this time. Instead, going into programming, and I'm going to bring up Spider 3. Okay. Now, I'm going to open a file which I have got on the desktop. I have Python, and I have distance. Now, this is a very interesting bit of program, because this shows you how the distance errors can creep in. So I'm going to run this. This has got spherical distance here and the ellipsoidal distance here. They are an implementation of the formula I mentioned earlier, the new formula. And I'm blowed if I can remember the name. So then we've got the Haversine formula here. This actually calculates the Haversine distance. So you've got the ellipsoidal distance, the spherical distance, and the Haversine distance. We're going to run that. So let's go up here and run it. and just run. And this tells me that the Haversine distance, and the distance I'm quoting now is going to be the distance between the Tower of London and the Arc de Triomphe. Okay, so the Haversine distance is 211 miles. The ellipsoidal distance is about 11,000 miles. The spherical distance is about 11,000 miles. Because those two are wrong, the formula I downloaded did not work. But there was one that I downloaded on my actual Pi Pico, which I should have with me right now, but I don't. And that gives me the distance of actually 206 miles, which is right. Now the distance in miles using the flat Earth calculation is 222. So we've got an interesting difference there. So 222 using a straightforward method that you'd use with a ruler and a map. That is not too bad. It's about 10% error over the 200 and odd miles. That is really not bad. The Haversine distance is about 5% error, which again is not that bad. The actual distance is 206 miles, and the new formula that I can't remember the name of is accurate to within half a millimetre across the entire globe. Not bad. Now I'm going to see if I can find that other bit of software. Probably won't run on this machine, so let me have a look. Pull that up. Python. Nope. What I've got now is a bearing calculation. Which uses the Haversine formula, which actually works perfectly for bearings. So let me open the bearing. Let's see. Why is it not showing up? Let's open all files. Distance, I've probably got a comma in it, that's why. Okay. Nope, not distance, is it? Open it again. It's me being me. I make errors, and I'm not bearing calculation. That's why it didn't put the PY after it. Okay, we'll open that. Now we're going to do the bearing calculation. Again, this is from the Tower of London to the Arc de Triomphe. It's not very far, about 206 miles. So we'll run that. And it tells us that it's 2.5 radians, 147 degrees, which is about right. And this calculation says 217 miles, but then I did tweak the formula for the ruler for the directions. So now we know the actual direction we're going in, and if I'd remembered my Pi Pico, we could have plugged that in, because I've got the formula for the new formula for the distance in that, and that would show up perfectly, and it's right. But I don't at the moment, and I'm not going to rush off to get it just for a quick video. But the new one is right, and I'll probably put the formula up. Well, actually I don't have to put the formula up, because I used a navigation library to find it. I didn't have to type all this lot here in for that. Now the bearing, that is really simple here. There we go. We have the location of the Tower of London there, the location of the Arc de Triomphe there, a little bit of basic maths here, cosines, sines and tangents. In fact, just cosines and sines. And then it comes out with the result in radians, turn it into degrees, and there you go, 147 degrees. So if you're in At the Tower of London you go 147 degrees, or bearing 147 degrees. You are going in 206 miles or thereabouts to hit the Arc de Triomphe. So, back to the studio. Ooh, where is that thing? There you go. Now that was really simple. And the formula I could not remember the name of is the Vincenti formula. And as I said, accurate to within half a millimetre. There's no point in my showing you the program to run the Vincenti formula. Yeah, I can tell you it's accurate to, it's 206 miles from Tower of London to the Arc de Triomphe. But the actual program to run the Vincenti formula is just, I include the library that says the Vincenti library, and then I just type Vincenti, enter the four coordinates, and it comes back straight away with the answer in miles. Not very exciting, I'm afraid. Anyway, there we go. So now you've seen that, and I'll see you again. This has been a British Tech Guru production, and I'm Zaphod Peoplebrox.